And we're back. So last time we went over basically how to check the conditions, and we reviewed a little bit for inference for regression and a little bit of what linear regression is like. This time we'll actually go over how to do the confidence interval. So like the 4-step process, our state plan do conclude. We'll do one example with data, with the same data as last time, and one example with computer output, which is actually even easier. All right, so here is our 4-step process. Notice the plan is a little bigger than normal because we have a lot more to check with those liner conditions. But again, in this state, we want to state what we're doing our interval for. So B is our slope, beta. So we want to say beta equals the true slope for the regression line relating y equals whatever to x equals whatever. And we just want to put the context in there and say what x and y are right from the beginning. You can put x and y in the other order, doesn't matter. And we want to know what our confidence level is, like 90%, 95%, whatever we're asking for. All right, this is called a t-interval for slope. All right, so it's just like when we were doing with mean, because this is like the mean slope. So it's like means that we use t. We are doing an interval, and we're trying to find slope. So it's a t-interval for slope. We may have to find some t-star values later on. All right, our conditions are linear, so linear. We want our scatter plot to look linear and no residual pattern. Independent, each trial needs to be independent, and the 10% condition of the population should hold. For our normal condition, the histogram of the residual should not be strongly skewed and should have no outliers. For our equal standard deviation condition, the residual plot should show an equal amount of scatter around the horizontal line at 0 for all x values, so over the x-axis and below the x-axis, and we should have a random sample or some sort of randomization. Randomization also works. All right, so if we're given two lists, like if we're given actual data, which is kind of rare, we'll put it into two lists and we'll go over to stat test, and at the very bottom, or towards the very bottom of the test menu is linear regression, t-int, t-interval. So linear regression, t-interval. All right, once you get your answer here, you want to state your interval and you want to state your degrees of freedom, which is n minus 2. Since we're working with two variables, we subtract 2 from our degrees of freedom. All right, and this also gives us all of our regular linear regression stuff. Like this gives us our slope and our y-intercept and our r and r squared and all that sort of stuff. So you can do this really whenever you want to do regression. All right, and it gives you a little bit more, like an interval for slope. All right, if we're doing this by hand or if we're given like a computer printout, we're taking the b from that and we're doing plus or minus t star times the standard error in beta. More than likely, this is the one you will be using. All right, so more than likely you will not be doing it by putting lists in your calculator. You will be using this formula. All right, the t star and the standard error of beta, t star you're going to have to find using inverse t, but the standard error in beta, that's given to us. So we really just have to do a little bit of work to get t star. All right, everything else will be given. So the computer output would be beta. Standard error is the standard error coefficient for the variable in the computer output. All right, it's in that chart. We'll look at it here in a minute. And t star is the inverse t based on the confidence level and the degrees of freedom, which again is n minus 2 now, not n minus 1. All right, and we are blank % confident that the interval from blank to blank captures the true slope of the regression line relating y to x. And make sure we'll throw some context in there. So sentence is pretty standard, just like before. All right, so here's the same data we had last time. So a random sample of 10 high school students produced the following results for the number of hours of television watch per week and GPA. Find and interpret a 90% confidence interval to estimate the true slope. So there it is. We want to estimate the true slope for the least squared regression line. And we want to find it and interpret it. All right, so let's do this. I'm trying to leave a bunch of space for the plan spot over here. So state we want our beta equals the true slope of the least squared regression line relating x and y. So let's see, x equals hours of TV watched, and y equals GPA. All right, so I've said what my variables stand for there, and our confidence level is 95%. All right, so we are doing a t-interval for slope. All right, and we want to check linear. All right, so L Is it linear? All right, so we need to look at the graph. All right, so let's see, second stat plot. I've already got the stuff in L1 and L2. There's my scatter plot and zoom 9. That definitely appears linear. So the graph appears linear. And we do want to look at the residual plot. So let's switch back over here and let's turn on another stat plot. Let's see, I've already got the histogram there. Let's go to L3. So we're going to turn this one on. We want L1 and residuals. So residuals, if you've done linear regression with it already, they're saved in the residual. So if you did the last one with this, they should already be saved there. And let's graph that. They're not going to show up because they're off the bottom here. Let's turn off the other one. Off. And now zoom 9. There's our residuals. All right, they look pretty scattered to me. We've got, what, 1, 2, 3, 4, 5, or maybe 4 above and 1 on the line, and 5 below and 1 on the line. So, all right, they're about even. I mean, it's about as good as we can hope for. As long as there's no pattern, I don't really see any sort of pattern here. So the graph appears linear, and there is no pattern in the residuals. Independence. All right, so 10, which is our N, is definitely less than 10% of all high school students. All right, so that checks out, N. All right, so now we want to look at the histogram. So we're doing, this is the normal condition. And we want the histogram of the residuals. So this one's a little weird. So let's go to the stat plot. And I'm going to turn that one back off, the one that we did with the residual plot. And back to stat plots. And here's my residuals. I'm going to turn this one on. And I want a histogram for the residuals. And the residuals are under list. Remember, so you go to the list, second list, and there it is, number 8. As long as you've already done some sort of regression with it, they will be saved there. And zoom 9. Let's see how that does for us. Oh, there we go. So there's a histogram. It looks pretty evenly split, right? But as long as there's no outliers and not strongly skewed. So the histogram of the residuals has no outliers and is not strongly skewed. So that checks out. E, we want equal standard deviations. All right, and we already basically did that when we looked at the no pattern in the residuals. There was the same amount of residuals above and below the residual equals 0 line. And I don't have much room here, but R is we did have random sample. Random sample stated. Whew, a lot of stuff happening there. So that was the L, I, N, E, and R liner. All right, next up. So this was lin reg t int on our calculator. So let's take a look at our calculator. Let's quit out of the graphs here. Stat, test. All right, it is a procedure, so it's under the test menu. And there it is, G, second from the bottom. All right, we've got L1, L2, and 95% confidence interval. So let's calculate that. And there's our interval right there, and it gives us a whole bunch of other good stuff like our degrees of freedom and our slope right there. It basically gives us everything. We could write all this down if we want, but we really want the interval from negative 0.0887 to negative 0.0554. So that's neat that all the values are negative. So we definitely have a negative slope here is what's happening. But they gave us a whole bunch more. So they gave us the degrees of freedom was 8, which is 10 minus 2, which we would have known anyway. They gave us our B value was the negative 0.072 that we had before. They gave us our A value, which was 3.89, which we had before. They gave us our R value. They gave us our R squared value. They gave us basically everything that we could ever want from this. So 0.926 for R squared, and it was negative 0.962, other way around, huh? All right, but we don't really need to write all. We really just need those two things, but if you want to write more, that's cool. All right, it's never a bad idea to write down everything they give you. All right, so then our sentence here. So again, for confidence intervals, we are confidence intervals. We are 95% confident that the interval from negative 0.0887 to negative 0.0554 captures the, so not true mean or true proportion anymore, now it's true slope of the, and then we can just go from here, the least squared regression line relating X, the number of hours of TV watched, to Y, which is the GPA. Voila. And since it's all negative here, like if we were doing a hypothesis test or something, and we want to know is the slope positive or negative, we have evidence of a negative slope. All right, we don't have any evidence of it being 0, so we definitely have evidence of linear regression happening. Whew. Yeah, this might be a long video, guys. Sorry ahead of time. All right, so another example, this one we're working with the computer printout. So here's our computer printout here. All right, so used cars lose value the more miles they are driven. Can we predict the price of a used Ford F-150 if we know how many miles it has on the odometer? A random sample, cool, random sample, of 16 used Ford F-150s was selected from among those listed for sale. The number of miles driven and the price was recorded for each. So here's our constants. This is our A. This is our B, miles driven. Here's the standard error coefficient stuff I was talking about. There it is right there. There's the one for slope. So this guy right here is the standard error in B. T values are prob, or sometimes this is just called P. That P didn't show up. There we go. That one's better. And that is the P value from hypothesis test we'll find later. There's our standard deviation for the residuals. Here's our R squared and R squared adjusted, which we're not really ever going to use. So what is the regression equation? Well, we are predicting price. So the predicted price is equal to A, 38,257 minus 0.1629 times the miles driven. There we go. And since I put in the words, I didn't have to define the variables. State and interpret the correlation coefficient. So what's R? Correlation coefficient is R. Well, we start off with R squared is 0.664. So R is the square root of 0.664, and we have to assign the sign. So since the slope was negative, R is also going to be negative. So now we just need to take the square root of 0.664. So second square root 0.664 gives us 0.815, I guess, or so. So negative 0.815. All right, so that means there is a strong, right, 0.8 is pretty close to 1, negative correlation between price and miles driven, or the other way around if we want. Remember, if we want to get linear, we need to look at the graph. What is the 90% confidence interval estimate for the slope of the regression line? Well, we're going to need a lot more room than this, so here's a whole new slide. All right, and we're also going to need some more information. So here is the regression line and the scatter plot. This is the residuals. And this is the histogram of the residuals. All right, it says residuals down there. All right, so that gives us everything we want. We've got this information here. Here is our B. Here is our standard error in B. We're going to need our t value, but we'll wait. And 90%, we'll have to find t. All right, but let's go ahead and try and just start here. So let's say our B is the true slope, or not B, beta. Beta is the true slope of the least squares regression line relating, let's see, Y is the price, and X is the miles driven of Ford F-150s trucks. Our confidence level is 90%. All right, our conditions. So let's see, we're doing a t interval for slope. You can say for beta if you want. All right, so we have definitely a linear graph here, and the residuals seem very scattered. So we have a linear graph and no residual pattern. All right, I, independence. So our n here was, how many, 16? 16, which is definitely less than 10% of all F-150s or F-150s for sale. N, normal. So we look at the histogram, doesn't seem to be skewed, and there's no outliers that I can see. So for the histogram of the residuals, has no outliers and not strongly skewed. We do have to put that word strongly, guys. I mean, for this one, we could probably just say not skewed because it's not skewed. All right, E equals standard deviations. So we're looking at the residuals here, and we've got about the same amount above and below 0, or we can look at the residuals here and say the same amount above. Actually, we're looking for each x value, but looks like we have the same above and below 0. Same amount of residuals above and below resid equals 0. And finally, R, we did say somewhere here that there was a random sample. There it is, so random sample stated. Check, all the conditions are checked out. Whew, lots of conditions there. All right, so now we can't do the linreg t stuff because we don't have the data. So we want to do B plus or minus t star times the standard error in beta. So we have B, it's given to us right here. We have the standard error in B, it's right here, right next to it. All right, we need t star for 90%. All right, so for t star for 90%, we have this t distribution. We want 90% to be in the middle. All right, which means we'll have 5% left over on each end. And our n was 16. So that means our degrees of freedom is n minus 2, since we're working with 2 variables, so our degrees of freedom is 14. So we can do inverse t with 0.05 and 14 to get our t stars. All right, let's move over so I can see what I'm doing here. So second distribution, inverse t to get our t. Our area below 0.05. Our degrees of freedom is 14 and minus 2. And our t star is negative 1.76, and the other one would be positive. So negative 1.76, and this one would be 1.76. So we get our b, which is this number here. So we're getting negative 0.1629 minus 1.76 times this 0.03096. And the other one is negative 0.1629 plus 1.76 times 0.03096. So we need to work out both of those. I know, it's a lot of work. I understand. Negative 0.1629 minus, actually, what is it? Plus, minus 1.76 times 0.03096. Close that parentheses. There's one value, and second enter to get the last entry. I'm just going to change this to a plus sign, and that's going to give us our other value. There we go. They're both negative. That's cool. I don't really have room for it down in that box, though. So I'm going to write it in my conclusion box. So it's going to be from negative 0.217 to negative 0.108. All right, so we are 90% confident that the interval from negative 0.217 to negative 0.108 captures the true mean, or not mean, true slope. I guess we could say true mean slope, but true slope of the least squared regression line relating y equals price and x equals miles driven by Ford F-150s. I know, not a lot of room here, but there we go. It's tough when you have to have all these pictures here as part of your conditions. All right, so that is how we do confidence intervals when we're given the computer output. I know it's not short, but hopefully nothing like this will show up on the AP exam. If it does, yeah, it's a free response. You can handle it. It's just a lot of steps. And there we go. That's the end of this one. One more video here for the hypothesis test, and we are done.